A beryllium atom has only 2 valence electrons in its outermost electron shell. They are both situated in the 2s orbital, as this orbital has lower energy than the 2p orbitals. The 2p orbitals remain empty. Since the electrons in the 2s orbital are paired, there are no single electrons to share with other atoms. Beryllium should not form any bonds. Yet many beryllium compounds are known in which beryllium forms 2 covalent bonds. Beryllium hydride, BeH2, is one of them. How can beryllium form 2 bonds? Evidently, one of the 2s electrons is excited to the 2p sublevel. In this way, single electrons are situated in 2 different atomic orbitals. They can overlap, at least in theory, with the singly occupied 1s orbitals of hydrogen atoms to form a BeH2 molecule. But if this were the case, the 2 beryllium-hydrogen bonds should be different, as they would involve different beryllium orbitals. However, experiments show that both bonds are identical. How is that possible? The hybridization concept assumes that one 2s orbital mixes with one 2p orbital to give 2 identical hybrid orbitals, known as sp, of exactly the same energy. The hybrid orbital is unsymmetrical. It consists of 2 deformed ellipsoidal parts, a larger and a much smaller lobe. The energy of a hybrid orbital is intermediate between the energies of the mixed orbitals forming it. Hybrid orbitals repel each other, just like bonding electron pairs. In this example, they are pushed apart as far as possible to be arranged along a straight line. The overlap of 2 hybrid 2sp beryllium orbitals with the 1s orbitals of 2 hydrogen atoms gives rise to 2 identical bonds. The beryllium hydride molecule assumes a linear shape with a bond angle of 180 degrees. Notice that valence bond theory combined with the hybridization concept gives the same shape of molecule as predicted by the VSEPR theory.
Electrons moving in atomic orbitals can be viewed as electromagnetic waves. Waves can interfere with one another. Interference of the electron waves associated with atomic s and p orbitals may produce a set of new, mixed orbitals of different energy and different shapes. These new orbitals are termed hybrid orbitals, and the process of orbital mixing is called hybridization.
A boron atom has 3 valence electrons. 2 of them are paired and are situated in the 2s orbital, while the remaining one is in a 2p orbital. In the excited state, one 2s electron is transferred to one of the empty 2p orbitals. Mixing of the single 2s with the 2 2p orbitals yields 3 sp2 orbitals. Notice that they are somewhat slimmer, as the contribution of the p orbitals is larger. Their mutual repulsion positions the hybrid orbitals in such a way that their larger lobes point towards the corners of an equilateral triangle. The overlap of the sp2 orbitals of the boron atom with the p orbitals of 3 fluorine atoms produces 3 boron-fluorine sigma bonds. The molecule formed has trigonal geometry and the bond angles are 120 degrees.